Okay, November 2023, paper 4, variant 3. Question 1. Oil of density 0.8 grams per centimeter cubed is poured gently onto the surface of water with density 1 grams per centimeter cubed. Describe and explain the final position of the oil relative to the water. If we describe what happens to oil, the oil stays on the surface. Okay, it stays on the surface. You can say it floats on the surface of the water. The explanation why, because it has a lower density. So oil has a lower density than water. So if anything has a lower density than another liquid, it would float on that surface than water. Let me write it down again, than water. Okay, an irregularly shaped solid object has a density of 2.7 grams per centimeter cubed. Describe a method to measure the volume of an irregularly shaped. So basically, you need a measuring cylinder. Okay, add water to a measuring cylinder. I'll just write it down as MC. This is a measuring cylinder, and take the volume. Volume V1. Okay, so this is the V1, this is the volume of the water. Okay, and then add the object, add the object to the measuring cylinder, add the object to the measuring cylinder, and take volume 2, and take volume 2, volume V2. Just subtract V2 minus V1 to find the volume. Yeah, that's easy. The volume of the object is 83 centimeters cubed. Find the mass of the object. Okay, so density equals mass over volume. Density equals mass over volume. So mass equals density times volume. You have the density, which is 2.7 times the volume, 83. The mass would be 220 grams. Question 2.1 is a graph that shows the extension of the spring. Determine the spring's constant. Okay, so spring's constant K equals F over X in which you have the force 14 and X is 4, so 14 over 4. This would be 3.5. The force is in newtons and the X or the extension is in centimeters, so the K would be newtons per centimeter. Newtons per centimeter. On figure 2.1, mark the limit of proportionality and label this point L. The limit of proportionality would be just around this point. This would be L. Limit of proportionality. Why? Because after the limit of proportionality, it's no longer a straight line. It's no longer a straight line. Figure 2.2 shows a car traveling at a constant speed around the corner A on a road. On figure 2.2 show or mark with an arrow the direction of the resultant force acting on the car. Acting on the car. So the force, if you're moving in a circular motion, it would be towards the center. Okay, towards the center of the rotation, which would be perpendicular to the motion. It would be in this direction. This is the force. Okay, this is the force acting on the car. We call this the centripetal force. And corner B has a smaller radius than corner A. State how the resultant force changes due to the traveling car around the corner of a smaller radius. If you have a smaller radius, then you need actually a larger force. You need a larger force. Larger force. Why? Because it's more difficult to keep the car in motion. Okay, the car could slip or whatever, so you need a larger force. As the radius decreases, the centripetal force increases. Figure 3.1 shows a boy throwing a ball at an object in a fairground. The ball has a mass of 190 grams, speed of 6.9 meters per second. Calculate the momentum of the ball. Okay, so momentum equals P equals mv. P equals mv, but the mass has to be in kilograms, so basically divide by 1000. So the mass is 0.19 times the velocity, which is 6.9. This is a momentum of 1.3 kilograms per kilograms dot meters per second. Kilograms dot meters per second. This is the initial momentum of the ball. After hitting the object, the ball bounces back. This is a keyword. Bounces back along the same straight path with a speed of 1.5 meters per second. The object has a mass of 1.8 kilograms. Calculate the speed of the object after it hits, or after it is hit by the ball. So we want to find the speed of the object. We want to find the speed of the object, which is v2. We have two objects colliding with each other, so the equation we'll be using is m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. The initial mass of the small ball was 0.19 times the initial velocity was 6.9. m2 u2 is 0. Why? Because initially it was at rest. It was 0, so initially it was at rest. Equals m1 v1. m1 v1. The mass of the small ball is 0.19 times v1 is... that's the question. v1 is not 1.5. v1 is not 1.5. It's moving in the opposite direction. So if it's moving in the opposite direction, so it has to be negative 1.5. This is the whole point of this question. To understand that momentum is... Okay, you need to understand that momentum is a vector quantity. It has two directions. So if it's moving in the opposite direction, it would have a negative value. This is negative 1.5 plus m2, which is 1.8 kilograms times v2. We need to find v2. We need to find v2. Okay, so let's start calculating. 0.19 times 6.9 is 1.3 equals 0.19 times negative 1.9. So 0.19 times negative 1.5 is negative 0.285 plus 1.8 v2. Please do not add negative 0.25 and 1.5. No, you need to remove this. Okay, just add plus 0.285. Okay, plus 0.285. Okay, so 0.285 plus 1.3. This would give you an answer of 1.585 equals 1.8 v2. 1.8 v2. Divide by 1.8. Okay, if you divide this number by 1.8, the velocity will be 0.88 meters per second. 0.88 meters per second. The kinetic energy of the ball is 4.5 joules before the collision and 0.2 joules after the collision. Calculate the change in total kinetic energy of the ball and the object during the collision. Okay, this is a nice question. Can I find the total energy of both objects before the collision and then find the total energy of both objects after the collision? Yes, I can do that. So simply, all you need to do is write down the kinetic energy equation 4 times, before and after. So before it was half mb squared plus half mb squared equals half, or you can say, instead of saying half mv squared, you can say half mu squared. Okay, half mu squared and half mv squared plus half mv squared. You can go on and say half m1 u1 squared plus half m2 u2 squared, half m1 v1 squared, and half m2 v2 squared. He said that the kinetic energy of the ball before the collision was 4.5 joules. So this is 4.5 joules. This is the ball. And the object was 0. The object was 0. After, it's not equal. It's not going to be equal. It's not going to be equal. Okay, why? Because the kinetic energy will change. 4.5 plus 0. After the collision, it was 0.2 joules. Plus, can I find the kinetic energy of the object after the collision? Yes, it is half. M2 was 1.2, so half times 1.2 times the velocity, which was 0.88 squared. So let's calculate this. Okay, half times 1.8 times 0.88 squared. This would be 0.696, okay, which is basically 0.7. 0.7. So 0.2 plus 0.7. This is the total kinetic energy after the collision. This is the total kinetic energy after the collision. Before the collision, it was 4.5. After the collision, it was 0.9. What is the difference? How can I find the difference? 0.4.5 minus 0.9. This would be 3.6. So basically, all I did was 4.5 minus 0.9, which is 3.6 joules. This is the change in kinetic energy. The change in kinetic energy. Question 4. The lowest possible temperature is 0 Kelvin. State the name of this lowest possible temperature. Okay, we know that this is the absolute value. Okay, this is the absolute value. Nitrogen boils at 77 degrees Kelvin. Calculate the boiling point in Celsius scale. So if it's Kelvin, can I convert it to Celsius scale? Yes, Celsius would be equal to Kelvin minus 273. Kelvin minus 273, basically 77 minus 273 would be negative 196. Negative 196 degrees Celsius. Okay? The temperature of a fixed mass of gas at a constant volume changes from 300 Kelvin to 400 Kelvin. State and explain in terms of particles the effect of the pressure of the gas. As the temperature increases, how does the pressure increase? Well, we know that the pressure increases. Okay, so the pressure increases. Why? In terms of molecules. In terms of molecules, they gain kinetic energy. So they move faster. Okay, so we need to say that they gain. Let's say that the molecules gain kinetic energy. Let's write it down. So molecules gain kinetic energy and move faster. When they move faster, what happens? They hit the walls of the container with a larger force, hitting the walls with a greater force. And you can say that they are hitting it with or more frequently. Okay, more frequently and more frequently. When they hit the walls with a larger force and more frequently, what happens? You can say that the pressure equals force over area. Okay, pressure equals force over area. So basically, the pressure increases. Okay. A sample of gas at pressure 120 kilopascals. The volume is doubled. The volume is doubled at a constant temperature. Calculate the pressure of the gas. Volume is doubled. Volume is doubled. So basically, you can say that when the volume doubles, the pressure halves. So the final answer would be 60. Is it that simple? Yes, it is that simple. Why is it that simple? So can I assume any volume? Can I just assume any volume? Yes, you can assume any volume. So you can say that the volume was, let's say, 1 meter cubed. When it doubles, it becomes 2 meters cubed. So P1 V1 equals P2 V2, right? So the new pressure, or P1 was 120 times volume 1, which was 1. P2, we need to find P2, but the volume doubles, so it becomes 2. If you divide by 2, 120 divided by 2 is 60 kilopascals. Question 5, figure 5.1. Okay, figure 5.1 is a scale diagram of wavefronts of red light approaching a gap in a barrier. On figure 5.1, draw 3 wavefronts after they have passed through the gap. After they have passed through the gap. So we can measure the wavelength and we can measure the gap. We would find that this gap is a narrow gap. Okay, this gap is a narrow gap. So if this gap is a narrow gap, how do we draw it? We draw it using a compass, and the pointy edge of the compass is at the center of the gap, opening up the compass to the first crest or wave front, and then you draw a semicircle on this side. Okay, and then you repeat the process with the 2 other wave fronts and draw, okay, 3 wave fronts. Okay, so these are the three wave fronts that have passed. Definitely you are drawing using your compass. Okay, draw using your compass. So these are the three wave fronts that have passed through the gap. This is a narrow gap. Okay. Moving on to the next question. Figure 5.2 shows the same barrier and gap. A wave of blue light approaches this barrier. Wave of blue light approaches this barrier. What happens when blue light approaches the barrier? On figure 5.2, draw three wave fronts of this wave before it reaches the barrier, three wave fronts after it goes through the barrier, after it goes through the barrier. So let's write down the colors. What are the colors? Roy Gibev, right? Roy Gibev. So red, orange, yellow, green, blue. So we have blue and we have red. We have blue and we have red. What is the difference between blue and red in terms of wavelength? Which one had the largest wavelength? Red had the largest wavelength and the violet had the shortest wavelength. So if we compare blue and red, if we compare blue and red, blue would have a shorter wavelength. Okay, a shorter wavelength. Can I draw wavefronts which have a shorter wavelength? Yes, I can draw waves which have a shorter wavelength. You can just measure the wavelength, the initial wavelength of the red. Okay, let's say that this is maybe 1 centimeter or whatever. If you measure the distance, okay, I'd draw three shorter wavefronts, okay, with a distance much smaller. Okay, you need to show that the distance is smaller. You need to show that the distance is smaller between them. Okay, definitely you're drawing them straight lines with equal distances between them. Equal distances between them. They have to be parallel. Okay, they have to have equal distances between them. And then as they pass through the barrier, okay, as they pass through the barrier, what happens? Okay, you'd say that the bending would be less. It's not bending, I'm sorry, that the diffraction would be less. Why? Because as you decrease the wavelength, the diffraction decreases. Technically, when you're drawing it, you will draw again three semicircular waves. Okay, you will draw three semicircular waves with almost the same bending. Okay, but someone, if you draw it, if you have these wave fronts which are very close together, if you draw them even shorter with an even shorter wavelength, you could technically draw them as straight lines. Okay, straight lines with bendings at the end. Okay, just bending at the end. So straight lines with equal distances which are bending at the end. You could do that if the wavefronts are very short. Okay, very close together. Yes, these are the wavefronts that have bent. Okay, wavefronts with the bendings at the end of them, indicating that you have a much less diffraction, a much less diffraction. Okay. On figure 6.1, sketch the current voltage graph of a filament lamp. The current voltage graph of a filament lamp. Okay, so on the filament lamp, what happens? We know that the filament lamp, the voltage increases, or basically the resistance increases. Why? Because it gets hotter. That's the explanation. We're gonna state this explanation. So, should I put the voltage on the x-axis or on the y-axis? It doesn't really matter. Honestly, it doesn't really matter. So if I say V/V and I/A, okay, so you have the voltage and the current. The filament lamp would always curve towards the voltage axis. It will always curve towards the voltage axis. Why? Because the explanation is that the resistance increases as the resistance increases. Okay, resistance increases as the temperature increases. Okay, as the temperature increases, so it curves towards the voltage axis. The voltage axis. If the voltage was on the y-axis, it would have curved upwards. It would have curved upwards. Now we have a weird looking circuit. Some batteries, some diodes, some resistors. Calculate the reading on the voltmeter. So the voltmeter is taking the reading of these two resistors, which are parallel to the battery. Basically, they have the same voltage as the battery. Okay, so what is the voltage of the battery? That's the question. Is it 15? No, it cannot be 15. Why? Because these batteries are flipped. The batteries are so this is the positive end and this is the negative end. Basically, you will subtract them. Basically, you need to subtract them. So 12 minus 3 is 9 volts. That's it? Yes, that's it. Because you have the batteries, they are flipped, positive and negative. So this is the total voltage of this battery. Calculate the resistance, sorry, calculate the current in the 4.2 ohm resistor. In the 4.2 ohm resistor, so you need to ask yourself, in which direction will the current move? In which direction will the current move? It will move towards the positive end of the larger battery. From the positive end of the larger battery. So it will move in this way. At this junction, it will pass through the 4.2 ohm resistor. It will pass normally. Why? Because the diode is situated correctly. So it will pass through the 4.2 ohm battery. Can I find the current? Yes, I equals V over R. I equals V over R. So basically 9 over 4.2. I equals V over R, 9 over 4.2, which is 2.1 amperes. 2.1 amperes. Okay, that's easy. Determine the current in the 2.1 ohm resistor. Okay, so I equals V over R. Can we do that? Can I say 9 over 2.1? No, you cannot say that. Why? Because you have a diode. You have a diode which is flipped. This is a flipped diode. It's looking in the it's looking at the other. It's looking. The current will not pass through this diode. It will not pass. So there is no current. Zero. Current in this diode is in this resistor is 0 amperes. Determine the reading on the ammeter. Okay, so the ammeter is the total current in this circuit. Okay, total current in this circuit is the current in the first resistor and the current in the second resistor. Basically, the current in the second resistor is 0 amperes. So the current in the first resistor is 2.1 amperes. So basically, you said 2.1 plus 0 is 2.1 amperes. Is it that easy? Yes, it is that easy. Can I find the power? Can I find the power in the 4.2 ohm resistor? Yes, power equals VI. Power equals VI. So the voltage is 9 volts and the current is 2.1. 9 times 2.1. Okay, so 9 times 2.1 is 18.9, which is almost 19 watts. It's 18.9, which is almost 19 watts. Okay, that was easy. Figure 7.1, okay, shows an electric field around point X. Okay, draw an arrow to indicate the direction of force on a negative point. Why? Okay, Y is a negative charge. In which direction will this negative charge move? Will it move inwards or outwards? A negative charge will always move against the or in the opposite direction of the arrows. Meaning that X is a positive field. So Y will move inwards. Y will move towards the center. While Y will move towards the center. You need to draw the arrow quite clearly towards the center. Arrow from Y quite clearly towards the center. State what is point X. X is a positive charge. Okay, X is a positive charge. A piece of plastic is charged by positively by friction. State what charge transfer occurs during this process. So when it becomes positively charged, what happens? It loses electrons. It loses, okay, electrons. That's it. Yes, worth 2 marks. Loses electrons from the plastic or whatever. You can say from the plastic. Yeah, from the plastic. but actually loses electrons is, okay, loses electrons is sufficient. Explain how the structure of an electrical conductor differs from the structure of an insulator. An electrical conductor has what? Has free moving electrons. Conductors have free moving electrons. Free moving electrons, while insulators have no free moving electrons. Okay, figure 8.1 shows the single turn coil in a DC motor. Explain the direction of the motion. Okay, the direction of the motion you're going to use the Fleming's left hand rule. Okay, Fleming's, okay, left hand rule. The first finger, the index finger, is from the north to south, so it's basically pointing to the left. The second finger, which is the middle finger, the current in this coil is moving into the page. It's kind of moving into the page. So using Fleming's left-hand rule, you'd find the thumb moving upwards. The thumb is upwards on this end of the coil, and the thumb would be pointing downwards on that end of the coil, which means that it will rotate in this direction. This direction, which is a clockwise motion. Clockwise motion or clockwise rotation. Okay, clockwise rotation. Why do you have a clockwise rotation? Because the force on the left part is upwards. The force on the left part is upwards, while the force on the right part is downwards. On the right is downwards. The coil is replaced by an otherwise identical new coil with 3 turns. 3 turns, and the same current in the coil. State how the turning effect compares with the turning effect in I. As you increase the number of coils, what happens to the turning effect? It increases. Okay, it increases. Yeah, increases the turning effect. The third coil, identical to coil I, except that the resistance is 3 times greater. The resistance is 3 times greater, meaning, okay, the potential difference is the same. State how the turning effect compares when you increase the resistance. When you increase the resistance, what happens? What happens to the current? Current decreases. So when the current decreases, what happens to the turning effect? Turning effect decreases. Turning effect, okay, decreases. It's slower now. It is slower. Okay, question B. I guess a lot of you would have problems solving this question, even though it's a bit easy. Let's take it easy. Now you have a voltage time graph showing the output of a simple alternating current. Okay, this is a simple alternating current, which is a sinusoidal wave. A sinusoidal wave. Figure 8.3 is the end view of a plane at time 0, and it's moving in a clockwise manner. It's rotating in a clockwise manner, meaning it will rotate in which direction? It's rotating in this direction. It's rotating in this direction. This is a clockwise manner. Okay, so let's just try to visualize it. What do I mean by a sinusoidal wave? Meaning that it will complete a full rotation. A full rotation. When? When will it complete a full rotation? After it completes a full wave. So at time t2, this means that it has completed a full rotation. Full rotation. Okay, so at time t2, this is a full rotation. What about if I want to say at time t4? If I come up with a new time, t4. T4 is only half a rotation, 180 degrees. What about t1? What about t1? That's the question in I. Draw the end view of the position of the plane at time t1. Include the labels A, B. T1, is it a complete rotation? No. Is it half a rotation? No. It's only quarter of a rotation. It's only quarter of a rotation. So when you are rotating in this direction, only quarter of a rotation means it will rotate 90 degrees. It will rotate 90 degrees. To rotate, so it would look something like this. A is on this side and B is on this side. That's all you need to draw. So at time t1, it will look somewhat like this: A and B. This is after 90 degrees. طب what about after 180 degrees, which is at t4? It will keep on rotating in this direction. So A will be facing downwards and B will be facing upwards. So this is at 180 degrees after half a rotation. This is at B. Okay, طيب. So at T4. What about at T5, which is similar to T3? T5 is similar to T3. What happens at T5? It's still rotating. It is still rotating. So B will be on the right hand side and and A will be on the left hand side. This is after 270 degrees. So T5 is the same as T3. They are both the same. Why? Because this is a 270-degree rotation. It's three quarters of a full rotation. Three quarters of a full rotation. A and B. Okay. Question II, he's asking about T2. Okay, so T2 is a full rotation. After we've completed a full rotation, T2 is a complete full rotation. Okay. So how will it look? It will look the same as the initial position. It will look the same. So A and B. A and B. It will look the same as the... Why? Because it has completed a full rotation. After it completes a full rotation, it will go on rotating quarter rotation. So at this point, if we say that this is T6, for example, it would be the same as T1. Okay, if I say this is T7, this would be the same as T4. T3 is the same as T5, which is at this position. It has completed three quarters of a rotation. So A would be on the left and B would be on the right. A would be on the left and B would be on the right. Okay, this is three quarters of a rotation. Question 9. For each application of radioactive isotopes, state and explain which type of radioactive isotope, okay, would be suitable and suggest an appropriate half-life for the isotope. To be honest, this is quite a difficult question. They don't ask that much about these questions, okay? They don't ask that much about these questions. But let's go on. Household smoke alarm. Household smoke alarm. They usually use alpha radiations. Alpha radiations. And I guess we've heard this before, but again, alpha radiations. Why? Because it's highly ionizing. We've probably discussed this before, that alpha emissions or alpha decay is used in the smoke alarms. Why? Because it is very highly ionizing. It is highly ionizing. The half-life, there was a question, um, don't remember which year, but the half-life was, I guess, around 60 to 70 years. Okay, if you say 60 years, that would be quite okay. Okay, it would be quite sufficient. Measuring the thickness of aluminum strips. Okay, so aluminum, whenever we say aluminum, we usually think about what? We usually think about beta emissions. Okay, beta particles. Why? Because beta can pass through. Okay, beta can pass through thin sheets. Okay, thin sheets of aluminum, but not very thick sheets. Okay, what about the half-life? Literally, you can say any number. Any number. If I say 5 years, would that be okay? Okay, no problem. 5 years. Again, the half-life of beta, we have never discussed the half-life of beta particles, so you can just say any number for the half-life of beta particles. Lead 208 has the highest nucleon number of stable isotopes of lead. Okay. Explain why lead is radioactive. Why lead 214 is radioactive. Lead 208 is has the highest nuclear number of a stable isotope. This is a stable isotope. Why is lead 214 radioactive? The thing is when you increase the number of neutrons, okay, when you increase the number of neutrons, the isotope or atom wants to decrease the number of neutrons. Okay, it's not stable. It becomes unstable as you increase. Okay, as the number of neutrons increases, increases, the atom becomes more unstable. Atom becomes unstable. So it starts to decay. Okay, it starts to decay, to reduce or to decrease the amount of neutrons. It becomes too heavy. Okay, if an atom is too heavy, it starts to decay by producing alpha or beta particles to decrease the weight, to decrease the mass. State two different sources of background radiation. We have the most famous source of background radiation, which is CMBR, cosmic microwave background radiation. Okay, cosmic um, radiation rays. Also, we have radon gas. Radon gas. You can say the food that we're eating, the drinks, we can say the rocks, the buildings, the trees, whatever sources around us. State what is represented by physics as the symbol H naught. H0, it is the Hubble's constant. Hubble's constant. Write down the equation. Okay, write down the equation for Hubble's constant. Hubble's constant is H naught equals what? We know that the equation V equals H naught times D, or you can say that H naught equals V, velocity, over D. What is the unit of H naught? That's a really interesting question. What is the unit of H naught? So if you think about velocity is meters per second and distance is meters. So if you divide meters per second by meters, you will have per second. That's it. That's it. So I can write down, okay, 1 over s per second, or you can write down per second. That's it. It's that easy, okay? Per second. Use this value h naught of to determine an estimate for the age of the universe in seconds, okay? So the age of the universe, to find the age, it would be 1 over h naught, which is 1 over 2.2 times 10 to the negative 18. That's it. Just plug it in your calculator. It would give you a huge number of 4.5 times 10 to the power of 17 seconds. Okay, we can convert it later on to years, which would be around 14 billion years. State when cosmic microwave background radiation was formed and where could we detect it from? Okay, when was it formed? It was formed, okay, during or after the Big Bang. Okay, it was formed. Okay, it was formed after the Big Bang. Where can we detect it? We can detect it literally in any point, okay? Can be detected at any point in space. Literally, if you look at any point in space, you will find this almost the same amount of these CMBR radiation. Okay? Okay.